Today we're working on conservation of momentum. It looks like we have a little bit of a typo here, but we're just gonna be fine. So before we get to the conservation of momentum problems, I want to make sure you get a good definition of conservation. It's a concept that shows up over and over in many different science classes. But the general idea with conservation is you have a system in which something is exchanged. And because all the objects in a system only interact with each other, the total amount stays the same. So I want you to picture conservation like conservation of money. Let's say I start with $100 and I'm super generous. So I give my friend $80. Well, because me and my friend are the system and the quantity we're exchanging is money, the total amount of money stays the same. In fact, I lost $80. She gained $80. We exchanged money only with each other, so the total remains $100. All right? Now, you might have heard conservation laws in plenty of other things, like conservation of energy. When a ball rolls down a hill, it is the ball and earth system. As the earth loses gravitational potential energy as the ball rolls down the hill, they exchange energy with each other, so the ball gains kinetic energy. You've probably seen it before with charge, too. In this case, when the balloon rubs on the sweater, electrons move from the sweater to the balloon, so the balloon gains electrons and might become negatively charged. And the sweater loses electrons, becoming positively charged. You've seen it with energy, you've seen it with mass, you've seen it with matter, and now we're just going to see it with momentum. In the mass case, maybe I had 300 grams in this container to start. So if there was 0.12 grams on this tray, then you can figure out how much is left in the container. So when we do conservation of momentum, it's going to be a system exchanging momentum. And there might be more than one object in the system, but the trick is it has to have at least two. You can't have an object just by itself. It has to have something to give that momentum to. So here's what a conservation of momentum problem might look like. And it looks like a lot of words and numbers to keep track of. Notice that you're always going to have at least two objects, which results in at least two masses. But then there's also the velocities before and after, right? So you must do as a first step drawing a before and after diagram. And in this type of diagram, I want you to draw all the objects with their masses and velocities labeled. What this is going to let us do is read really quickly what each individual item's momentum is. So the block is sliding frictionlessly to the right across a horizontal surface. It collides with a ball at rest. The two objects stick together after. This is an inelastic collision. So maybe in my final picture, I'll draw them together. Hey, what would be their total mass if they were stuck together like that? Right? A 2 kilogram block and a 1 kilogram ball. So together, these two things act like 3 kilograms total. So maybe my picture looks something like this. Step one for a conservation of momentum problem, I want you to draw. Because for step two, I want you to calculate the momentum of every object in the system. And with this type of diagram, that makes it really straightforward. You get a point for doing this equation, MV, with symbols first. So don't skip that step. Even if you look really closely and you're like, okay, the ball is not moving, its momentum is 1 times 0, it's 0. Oh, so at the end, I don't know the final velocity. I know the mass is 3 kilograms total, but I don't know VF. The idea with conservation of momentum is these two objects are in a system together. So the momentum in the before picture has to equal the momentum in the after picture. Hey, wait, but now I can really easily solve for the final velocity. Dividing by 3 on both sides, I have a final velocity of positive 2 meters per second to the right. So I calculate P equals mv once for each object. And that's one of the benefits of doing this type of drawing, right? Because then I just get the momentum of each one. Then I set momentum before equal to after. And finally, solve. Solve for the missing velocity. Here's a good check at the end of a problem. I know the momentum before and after have to be equal. So initially, I do the mass times velocity of the red rectangle to get 6 Newton seconds. But the ball has 0 momentum to start. At the end, this one's mass times velocity would be 2 times 2 is 4. This one's mass times velocity, its momentum is 2 times 1 is 2. So is it true that 6 is equal to 4 plus 2? Cool. Here's another check you can do. At the end of a problem, I mentioned that the two objects exchange momentum. So doesn't this picture look a little bit like this one? The total stayed the same, but they exchanged momentum with each other. So in this case, red loses some momentum. Blue is going to gain some momentum. But all in all, the total remains 6. Now let's try another one, and we'll go a little faster this time. I have 2 football players in an inelastic collision. I have one player running to the right at positive 6 meters per second because it's to the right, a 100-kilogram player running to the left at 3 meters per second. So remember that's going to be negative. Again, they stick together and we want their final velocity. As I'm doing my drawing, I have to be careful of right and left. So I've got my 60-kilogram football player running to the right at 6 meters per second, but my 100-kilogram player running to the left would need to have a negative velocity. Both momentum and velocity are vectors. Now, they have an inelastic collision, and you've seen my drawing skills. They kind of tumble together to make a total mass, because they stick together, of 160 kilograms. But I don't know which way they're going. Um, if I just draw an unknown velocity vector here, that's sufficient because I don't know if it's going right or left. But let's say that I figure out at the end of the problem that VF is negative, then I just change my picture. If VF turns out to be negative at the end of a problem, that just means it's going to the left. So now let's do the thing. Let's calculate the momentum of each person in the system. So the momentum of player 1 is 60 times 6, or 360 Newton seconds. Player two's initial momentum, its mass times or their mass times velocity is 100 times negative 3, or negative 300 Newton seconds. At the end, they stick together, so their total mass is 160, and I'm trying to find VF. So if I solve this equation, on the left, there is 60 Newton seconds of momentum. And on the right, there's 160 VF. Dividing both sides by 160, VF ends up 0.375. Because this number came out positive, I know that they're moving together to the right. And actually, at quick inspection, this makes sense because there was more momentum going to the right initially than there was going to the left. So again, we do our drawing. We calculate P equals mv for each object. We set momentum before equals to after. And finally, solve. I'm going to end up with some algebra equation which should be solvable. To find VF, I'm going to divide by 160 on both sides. And we can do a little bit of a check, right? I should see that one object is, or one object in the system is losing momentum, and the other one's gaining momentum. It's becoming more positive. In fact, if we do out this math, look at just red. This person's initial momentum was positive 360, and their final momentum would be the 60 kilograms of mass times 0.375 is only going to be 22.5 Newton seconds. So to add impulse to this idea, red loses momentum because there was an impulse. The force applied for some amount of time by blue made red lose momentum. How much momentum did they lose? That's impulse. And same for blue. So if I do the momentum before and the momentum after, I get the momentum changes from negative 300 to positive 37.5. Impulse is the change in momentum for a single object at a time. So last one, this is about the hardest I can ask. Elastic collisions are about the hardest I can ask because then if objects bounce off each other, you end up with two masses, definitely, and four velocities. At rest, 30 meters per second to the right. This is negative 25 to the left. So let's say I've got this person that leaves their car near the baseball field, but it is not having its brakes engaged. All these problems assume that objects are free to move, but if their tires were having traction with the road and the parking brake was engaged, the car wouldn't actually roll because of an external force. So we're going to make this nice assumption that as this is traveling, or as this system is interacting, that all the objects are free to actually move, right? So notice in my after picture, the ball is moving backwards at negative 25 meters per second. So I have to have that negative number. And I don't know the final velocity of the car. So we drew our picture. Now we calculate the momentum of each piece of the puzzle. The momentum of the baseball to start was 0.5 times 30, or positive 15 Newton seconds. But the car is at rest, so that's 0. After the collision, that would be 0.5 times negative 25, or negative 12.5 Newton seconds to the left. We know the car's mass is 1,000. We just don't know VF. So here's the algebra equation I'm solving. There's 15 Newton seconds of momentum to start. If the ball bounces backwards and has negative momentum at the end, that means the car has to pick up extra momentum. So this is algebra. We're going to add 12.5 to the right. That means 27.5 Newton seconds of momentum goes into the car. Divide by 1,000 on both sides. And the velocity of the car is 0.0275 meters per second to the right. One object lost momentum. That was the red object. It went from 15 Newton seconds to negative 12.5. It lost momentum. As a result, blue had to gain momentum. It started at zero, and now it's moving at 0.0275 times 1,000. One gained momentum, one lost momentum, so the total stays the same. That's conservation of momentum. Good luck, everyone.